Been a lot of progression over the last year. For example, Ford, Nissan, and Daimler signed an agreement in January for the mass production of fuel cells. So this technology is going to get cheaper with this implementation. That's in Vancouver, Canada. Also, Ballard signed a deal with Volkswagen actually in the last month about a research and development for fuel cells in their vehicles. As well, Hyundai actually is going to be mass producing their fuel cell vehicles by 2015. Also, Intelligent Energy and Suzuki have signed a deal. They actually have a plant for their fuel cell vehicles, and it will be producing in the future. GM also recently closed their research center for fuel cells in New York. They actually reopened it in Pontiac, Michigan, closer to their transmission and engine development areas so that they can work better together. They're also hiring over 80 positions for their powertrain division. Also, the U.S. Department of Energy is funding $3.4 million towards a community in Houston that are making fuel cell trucks to lower the emissions in the area. There is a wide variety of mobile applications in fuel cells. There's been, like, with Boeing's fuel cell plane, there's also been fuel cell motorcycles, fuel cell vehicles, forklifts. They're very lucrative and cost competitive in this market. And they're definitely, you are going to be seeing them in the future.
Including a fuel cell golf cart, which we previously built. So, for people that are wondering a bit about the limitations of fuel cells, if they can really compete at all in the speed and power that's produced by internal combustion engines, there is a company in France called Green GT that has produced a massive race car that can produce about 540 horsepower from its fuel cells and reach a speed of approximately 188 miles per hour. We're not going to be going quite that fast, but something to strive. To give you a bit of an idea about our system, currently what we have is a lithium-ion battery pack going to a controller for a motor, which then powers the drivetrain. That's pretty similar to a lot of the systems that we're seeing in the zero emissions category. But what we're proposing is to add onboard fuel storage, which would be hydrogen tanks, which then go to a 17 kilowatt PEM fuel cell, so having a polymer electrolyte membrane fuel cell stack. This would then produce up to 17 kilowatts of power, go into a programmable logic controller, and this PLC would then send it right onto the controller if the motor is asking for less than 17 kilowatts. If it's asking for more than that, the battery pack will kick in and help out to provide the rest of the power. Now, on startup, one of the main issues with fuel cells is that you have to make sure your temperature is right. And the competition states that you have to be able to start your vehicle within 10 seconds and that you cannot use a preheater. So what we have is this lithium-ion battery pack can actually produce enough power to run the snowmobile right away while using a heater during operation, which will bring the PEM stack up to temperature. That temperature is not super high. It just needs ambient air around it at -5 degrees and above. So we're not looking at getting it up to 100 degrees Celsius or anything like that. If we're in -20 conditions, then we need to have it hot enough.
So the motor that we chose is the AC35 by HPEV with the 1238 motor controller. We chose this motor because we need enough power to actually get enough torque out at the track to move our sled. Our sled will be approximately 500 kilograms with the fuel cell systems on it. So that's about 200 plus more than an electric vehicle. So we needed enough torque and also an AC motor that was powerful and had enough continuous torque for us to move efficiently with it. Also, we're using a two-stage transmission. First is the Gates Polychain GT carbon belt. Chose it because it's very efficient and not as noisy as a chain drive. We also have the second stage is a train drive. And the reason why we implemented it this way is just because it's easy. It was the easiest way to get to this competition, and to, also this motor is very large and has space limitations.
So to give you an idea of the power requirements of our system, as they all need to match up for it to work perfectly, we have the motor controller demanding approximately between 72 and 96 volts. It can handle up to 600 amps of current. Now, the battery packs will fit in that range, as the nominal voltage of the batteries is just under 96 volts. And the current produced is 0 to 450 continuous, or 750 pulse, which we will never have to reach, as the motor controller limitations are below that. The fuel cell stack, however, produces only 40 to 80 volts with 0 to 380 amps. So the way that we're going to get that voltage up higher, we have two possible options. We can use a DC-DC step-up converter, which is harder to source as it is quite large, needs to handle 17 kilowatts. It's approximately $1,000 a kilowatt. So that option is less appealing. Or putting a smaller pack of batteries in series with the stack, which would bring the voltage up to the necessary range.
So the batteries that we decided to go with, we have 26 Houghton lithium polymer cells that we're currently using. The voltage ranges of this cell extend from 2.7 volts to 4.2 volts, with a nominal voltage of approximately 3.7 volts, which gives you a total pack voltage of 96 volts. You have a max discharge current of 450 amps and a max charge current of 225 amps. So that gives us a very broad range to work with. And with the calculations of 75 amp hours per cell, we get about 7.2 kilowatt hour in the entire pack. The reason why we decided to go with these batteries is because of the minimum discharge temperature for these batteries. With these batteries, we can go up to minus 30 degrees Celsius, which is about minus 22 degrees Fahrenheit. If you look at the graph here, at minus 20 degrees Celsius with 100% pack capacity, we can go down, we still have the nominal voltage of the pack at 3.5 volts, which is very close to the 3.7 volts that we need. As the pack does heat up, we will move up to different bars, obviously, so we can probably, we're hoping to operate at about higher than 0, so about 25 degrees Celsius once the batteries do get a chance to heat up. So as you can see, the voltage there, it looks pretty good. It's about 3.7, and it does drop as it does discharge with any batteries.
All right, I'm Jay, and I'm the so-called fuel cell manager of the team. So as mentioned before, we are using a proton exchange membrane fuel cell. Some of you may have heard of this, but for those of you who haven't, I'm going to give kind of a brief, simplified introduction of what they are. So our system will be using compressed hydrogen at approximately 99.99%, which is a lot less pure than that is previously required fuel cells. So basically what the system will use is the compressed hydrogen and the oxygen from the air will combine to create electricity, water, and heat only. So this is a completely zero emission vehicle. Each of the cells are combined in series to increase the voltage up to our 40 to 80 volts that our fuel stack operates at. And as I mentioned, this is a zero emission energy source, and this is why we think it is a wonderful technology for this competition, as it is clean as are the batteries, but will offer a kind of a competitor to all the other battery competitors. So the fuel cell that we have actually sourced is Hydrogenics HYPM16. It has a 17 kilowatt maximum output with an efficiency ranging from about 50 to 55%. This entire fuel cell module that we have ordered incorporates a number of systems, such as internal humidification and all the flow meters required, the blower to grab all the air from outside. This makes it much more safe and easier to regulate, as we have not done all these systems ourselves. All of the connections are certified by Hydrogenics and will make the certification by potential judges here much easier. This, operating at maximum capacity, it will consume approximately 240 liters per minute of hydrogen, and will add approximately 220 kilometers to the range of our snowmobile, which far exceeds any of the current battery-powered facilities. So the tanks we are using, some of you may have seen our display with the big funky looking tanks on the end. They're quite large. They are 700 bar Dynatech tanks. You can see here the dimensions, 1.2 meters long, about 30 centimeters in diameter. They are made from extruded aluminum wrapped in carbon fiber. The carbon fiber will allow any impact to be, the energy from any impact to be dispersed along the length of the tank. And this tank is also includes an integrated solenoid valve. This allows for less moving parts and less opportunities for leaks. And also there's a safety measure incorporated into the tank where if there's ever a shortage of electricity to the tanks, they will shut off and no electricity will be provided to the fuel cell. This is kind of a great safety measure so that if anything malfunctions in the batteries or anything is going wrong, we are sure that nothing will be delivered to the fuel cell.
So for fueling costs, we did a bit of research here. Now, things have changed a lot in that you used to require much more pure hydrogen to avoid degradation. At the moment, our power module only requires 99.98% pure hydrogen, whereas some in the past have been up to 5 nines after the decimal. Fueling costs have been stated to be approximately, or to be under $15 with as low as $5. Depending on your source, you could use solar power, you could use steam reforming, you could use nuclear. Depending on how you achieve that hydrogen, then it will cost a different amount. Even at 15, that's quite competitive for the amount that we need to store in our vehicle. We're looking at approximately 4 kilograms of storage. So it requires $60 to fill our entire vehicle for a long trip. There was actually a station in Norway which was selling hydrogen at $6.40 per kilogram a couple of years ago at 700 bars, which is a necessary pressure for us. The infrastructure. Obviously, if you have a vehicle like this, you need to fill it up. There are currently many countries that are working on this infrastructure, the States being one of the primary ones. In the US, there are currently over 50 stations, 10 of which are currently open to the public to actually go fill up. Most of those are in California. Michigan actually has the first station that was made in the States and is still operational in Dearborn, Michigan, and it is owned and operated by Ford Motors. Canada also has stations. They have a 7-node highway from Victoria to Whistler, and that was actually used during the 2010 Winter Olympics to fuel the bus fleet that drove all of the Olympians back and forth from the various events. Another one is Germany. Germany has 15 stations that are currently open to public, with many more private ones, and they're expecting to raise their number of public stations by 50 stations in the next 2 years. Japan also has many stations and is expecting to raise their number by 100 by the end of 2015.
Okay, so we kind of developed this sort of sense of how you choose what type of snowmobile you want and what they will be able to operate with. So we kind of came up with this triangle here with the main factors being low cost, long range, and low emissions. And so our motto here is kind of, you can only choose two. So with the internal combustion engine, obviously they're the lowest cost, and they have one of the longest range, arguably with our fuel cell design competing. It cannot choose low emissions. We all know that. They are kind of why we're doing this whole sort of competition. The next is the electric vehicle. We know that they are definitely less expensive than what our fuel cell will be. It has no emissions, but it does not have that long range that we are really striving for. So for us particularly, we were looking for something that research centers can use for sampling data, and we could not skew results. So we needed a low emission vehicle that could have that long range. Although our cost, that we have a very high cost, we do meet these two criteria, and this is why we are choosing this type of vehicle for our design.
To give you a bit of an idea of that cost, our battery-powered vehicle, if we were to only construct one, I'm not talking about mass marketing, it would cost us approximately $33,000 the way we have currently designed it. Our fuel cell snowmobile with battery hybrid design would cost us approximately $106,000. Now, internal combustion engines have reached economy of scale. They do have mass marketing. There are those savings. Fuel cells, once they reach that, we do expect that to come down significantly. We don't know if the cost will hit the same as an internal combustion engine, but we do know it'll be much lower than that. We were even quoted for our power module. They told us if you even bought 10 of these instead of one, we would give you a significant discount, because it's just the numbers aren't there yet to mass market. Okay, so now into performance. I'll talk a bit about the range here. If we were to travel at, these are hypothetical, based on calculations as we have not operated either of these vehicles. To run our electric snowmobile at 24 kilometers, at 30 kilometers an hour, we would only be able to go for approximately 48 minutes or travel 24 kilometers. This is not nearly enough compared to the internal combustion engines, and it also requires a long charging time. You need to plug in your vehicle versus fill it up. It's not really practical. With the hybrid fuel cell snowmobile, we're expecting a range of approximately 246 kilometers if we were to use the two 700 bar tanks that we have described. This range is very competitive with the internal combustion engines, and it would have a runtime of approximately 8 hours and 11 minutes. And then all you would have to do is spend 3 minutes fueling at a station, just like at a gas station. Also, these are assuming good but not optimal snow conditions. Here is a company called Quantum Technologies, which actually constructs hydrogen tanks. And they have done some very severe abuse testing to their tanks to validate that they are safe. Here's a list of some of the tests that they perform, including acid environment, extreme temperature, bonfire, which actually another company called Ballard has tossed a tank into a bonfire before, and there is a video online. We don't have it in our presentation. And when it did finally cause enough damage to rupture, or they may have even had to force the rupture, it nearly put the bonfire out because of the rapid release of hydrogen. It actually pushed all the oxygen away, and there was not enough oxygen to perform a ton of combustion, and it very nearly put the fire out. They have gunfire penetration tests, which have passed, drop tests, etc. And here's another tank safety series of pictures. The idea here is that because hydrogen is so light, what happens is if you have a leak in your hydrogen tank, even if you create a spark for it, you will end up with the hydrogen rising so quickly, you will just get a burst of flame. Actually, here you go. So the left side is the hydrogen tank. It's bursting as the tank empties itself, whereas the gasoline tank is currently, it leaked at first, and then the fumes became flammable, and then when it was sparked, it had built up all of the gas on the ground, and here we go at 3 minutes. The hydrogen is finally dying down, your tank is almost empty, the gasoline vehicle isn't having such a good time, and then that final one, you see that the hydrogen tank on the left is empty now. The driver is saying, oh, I'm going to have to go get a new tank to refill, but they're safe, whereas not so much with the gasoline. Oh, and then that's describing how the tires are rupturing and sending the refill. Sorry about that.
So just to go over quickly some advantages and disadvantages. We know that the fuel cell system still needs a lot of work. There are disadvantages. One being the high cost. This is being addressed by a lot of the major car companies by mass producing this technology. Hopefully in the future we're looking to have a lower cost fuel cell system. It is a complex system. There are many research centers all over the world that are working on making each part of the fuel cell process more efficient as it goes on. It's also a little bit complex to implement into a vehicle. It takes a lot of engineering. The lack of hydrogen infrastructure is also a negative, as we've shown in this presentation. That is improving, and by switching focus from gasoline to hydrogen, we can actually effectively increase our hydrogen infrastructure. The safety part of it, the disadvantages are definitely the high voltages that it runs at. but which is very similar to the electric snowmobiles that we already have here. We know that electrical safety is very important. Temperature and startup limitations. Fuel cells do have some limitations with this, but we're hoping to prove to you by next year or the year after, or whenever we can prove to you that this is a safe technology, that we want to show you that we can run it in Michigan. But the advantages are, again, zero emission. Water is the byproduct of a fuel cell. We have a longer range, a ×10 magnitude of the electric snowmobiles, theoretical, of course. Safety, we've proven to you that hydrogen fuel cell tanks do have high safety measures and standards. Refill time, Mercedes-Benz actually has quoted themselves as 3 minutes to refill about 4 kilograms of hydrogen in their tanks. So that's a very short time, especially compared to recharging the battery. And fuel abundance. We can make hydrogen by process of hydrolysis, and hopefully in the hydrolysis process, they're using renewable energy, so this process is completely renewable.
And even if you were not to use electrolysis, there's already an abundance of released hydrogen in every single fuel refining area right now that could be harnessed as we're slowly implementing the renewable energy sources. So at this point, we'd like to thank our sponsors and you guys for listening, and we'd like to open the floor for some discussion, questions.
You know I'd be first, right? Why design a 1,400-pound sled that goes 246 miles?
Because we are designing this for research center uses where they cannot, we were thinking of it as you cannot pollute your own results when you're taking tests for pollution at the Greenland Research Center that it's been designed for. And we figured with 30 kilometers of range, it's kind of pointless. You could probably take a dog sled that far. You need to get enough range that you can get there, back, and that you don't have to spend time charging it. We want to be able to refuel it just like an internal combustion engine. We want to have all of the benefits of an internal combustion engine, like range and quick refueling,
Right,
without the emission.
I hear you, but I think you're over-designing is my point. You're designing it to go much farther than we've asked, or that the customer's asking, at the cost of a very heavy system with a very large fuel cell. And I would ask you to consider a much more modest design so your sled doesn't weigh more than the 1,000-pound lead-acid battery sled that we had here a few years ago.
That's very fair. A lot of that decision has been based on what we have available. We were donated our sled from Bombardier, so we already had a long Tundra sled. Mind you, we could still have used smaller components on that, but with our stack decision, that was largely based on the fact that Hydrogenics, the company providing it to us, had just come out with this newest generation. It was their top one. We already decreased that from an expected 30 kilowatt stack, and we realized that that's completely unnecessary. We brought it down to almost half the power, and they're quite happy with this power module. We get temperature ranges that
fuel cell is still more expensive than the batteries we're buying, right? That's a $20,000.
Sorry?
That's probably a $15,000 to $20,000 fuel stack, right?
Yes.
Yeah. Yeah.
It's not.
So I'm just saying there are companies that make 5 kilowatt, 10 kilowatt fuel cell stacks that balance full balance of plant for much less money.
And of course, eventually the balance of plant will also be one way to save a ton of money, because if we look at our 17 kilowatt stack at approximately $40,000, and we look at a 17 kilowatt stack that doesn't have a power module, doesn't have balance of plant around it, you would drop that to about a quarter of the price or less, $10,000.
You haven't talked about the balance of plant
Yeah.
in your presentation, right? Did I miss it?
Well, we talked about the internal humidification, the mass flow controllers that will be hooked up through the PLC to the motor controller.
I'm talking about the cooling.
Oh, there's usually uses the glycol cooling system, which will require the pump. So as we spoke yesterday, that does raise the concern for the noise, and I'm sure that's kind of
what you get rid of 17 kilowatts of heat.
Yeah. So The fuel cell has been tested obviously at normal operating conditions at 25 degrees Celsius, and it can obviously cool it fine. But at the temperatures we're talking, it's going to be even easier. The blower will not need to work as hard. And also a thing that has been addressed, I know there's been some skepticism about kind of the snowmobiles being too quiet. A lot of people have been saying it's almost eerily quiet. That poses a threat of kind of danger if someone's driving and you can't even hear them. And
yours won't be quiet. Yours won't be quiet. Cool.
Exactly.
So
Yeah.
Someone will hear us coming around the corner.
The radiator is a big deal for cooling that. You have to build a radiator big enough to cool the pack at full power.
Mind you, though, Hydrogenics has said that they will help us source the correct radiator, and that they're not expecting it to be much more than a couple $100. But another thing too is if we're producing 17 kilowatts of power at 50% efficiency, we have 17 kilowatts being rejected as heat as well. But if you have an internal combustion engine producing 17 kilowatts of power at 20% efficiency, you've got 17 times 5 times 4 kilowatts being repelled as heat as well. So we're going to have a
But it
quarter
goes
as
out the
much.
exhaust and away from you, whereas
Yes,
the fuel cell,
yeah.
it stays right there under your seat.
It is, yes, it is going to be an issue that we have to tackle.
Yeah.
But it also operates at 50 degrees Celsius, so with ambient conditions, you will have quite a bit of convection going on.
Then you try to make it quiet, put insulation around that heat. And yeah, I'm just saying, I think you should scale back. That's all I'm saying.
And that's very fair. We don't need that power. We do want that storage. We still would like to keep the storage because your range won't really decrease as we decrease the size of the stack. We keep the same size of tanks. But since we haven't purchased the stack, that's actually still very much adaptable as Hydrogenics comes out with better piling modules and other companies as well.
We come off it. Don't take this as an attack, but the guys who have actually done some work with fuel cells are telling you that there are inherent problems. We've been running a fuel cell on the Arctic for a few years now, and we have frozen it a few times, which is pretty much the end of it. So another thing to consider, since water is the byproduct, is how would you get through something like the cold start event where your fuel cell has to be turned off overnight in freezing temperatures, stuff like that. It's not a trivial thing.
Our fuel cell module that was provided, there's actually a normal operating temperature shutdown and a cold temperature shutdown procedure. So there are kind of instructions and everything that is required to follow for us to shut down up to negative 20 degrees Celsius. So this obviously involves things like purging with oxygen and everything to ensure that all of the water is released from the cell, which is hard to do to make sure every ounce of water is released, but they do have a strict procedure for making sure that these things can shut down at negative 20 Celsius and will be operable the next time we start.
Okay.
And it has a storage temperature of minus 30 or minus 40. There's two stacks we're looking at, sorry. One of them has minus 30, one has minus 40. But we believe that minus 30, while still potentially being crossed sometimes, if you're careful of how you store it, you might be able to make that reasonable.
Okay. Another criticism of fuel cell technology, not your design necessarily, because as you pointed out, you can make the hydrogen from electrolysis, but the fact of the matter is that over 90% of the hydrogen you get now is made from natural gas. So you're not really getting away from fossil fuels. There's still a tremendous amount of environmental impact associated. It's just not right for your snowmobile.
Absolutely, and that's one thing that we need to make sure is differentiated. Hydrogen fuel cells are not a power source. It's almost more like looking at water or hydrogen as a battery. You're putting power into it, into water for electrolysis. You're getting out hydrogen, but that power has to come from somewhere. You're moving it. So essentially what it's allowing though is that right now, while we're still transitioning the energy that we're deriving from, say, coal or burning fossil fuels of any kind into more wind, solar, nuclear. Quebec's got 85% hydro now. as we're moving that over, we'll keep getting greener and greener, or cleaner and cleaner hydrogen power coming out of our snowmobile. And it's the same thing for the batteries though too. You have to charge those batteries. And if they're being plugged into a wall that goes to a generator down, or a station, and it's a nuclear one or it's a solar one, it might also be a coal one. And we don't know if that energy, well, you can find out if that energy is green or not, but it's not inherently a green energy source.
And one final comment. You're running on pure hydrogen, which means that you don't have to have an onboard reformer, which is probably, it may be an essential design consideration. But one of the concerns, of course, is the hydrogen compressed to 10,000 psi. So, I mean, there are PM fuel cells that might run on methanol and things like that. Is that a possibility?
It's not a possibility, but we are definitely leaning towards a hydrogen fuel cell. We do have a fuel cell research center in Kingston where they're working on many different ones, and I know one of our profs is working on a lot more reformed hydrocarbon fuel cells. And it's not out of the question, but we would think that it might be more of an intermediate stage, as eventually we want to sort of be implementing the entire water cycle aspect into it, where you just put clean energy into water, get out your hydrogen, put it in, turn back to water, and just rinse and repeat, as versus still needing to have fossil fuels that are then reformed.
Well, I think that's an admirable goal. Of course, it takes more energy.
Yes,
Out of water than you get back out of it.
Yeah, so it does reduce the overall. Are there any other questions? Okay, go ahead.
You said told that you start with the lithium batteries.
Yeah.
Then when the fuel cell warmed up, you switch to fuel cell.
Correct.
And if you need more power, you get a boost from the lithium batteries.
Yeah.
When you're running on just a fuel cell, will it recharge the lithium batteries?
It can be implemented. We can't charge and discharge at the same time. So
No, you're not using lithium batteries now, you're running on the fuel cell.
Yeah.
Will it go back to charge the...
That is the goal, is to have that implemented, as it would be far more efficient than having that plug in when you get back to your house.
We're thinking of using the PLC that we're going to be using in order to do that, because we know that we can't discharge and charge batteries at the same time, but you can't implement a simple switch that can split the power using the microcontroller that we are going to be using.
And also, our max continuous speed does not require a power output from the fuel cell that is near its top range, so we will be able to siphon off some of its power to the batteries and go at our max continuous speed.
So let's assume that we could take care of all the safety issues. How would you ever propose that you could compete in this event without expecting KRC to put in a hydrogen plant?
Yes, there are refill stations, sorry, in Michigan, or approximately 7. Most of them are privately owned, not open. So we would either have to go public ones, or we would have to work some sort of deal with, say, Ford and Dearborn, and fill up on the way, bring extra tanks. Tanks are expensive, so we might very well use smaller tanks even, ones that can't handle as high of a pressure, and fill up with those just to prove the point until infrastructure is there.
And the temporary solution would be to use a portable filling station. But I say temporary as I say temporary for the reason being that as the infrastructure increases, the requirement for these will obviously go down. So it is something that we could do, but obviously if we can get access to some of these fueling stations, it would be our ideal scenario.
So those tanks you have, are they just cylindrical pressure vessels, or are they the metal hydride matrix inside?
No, there's no metal hydride for this. We decided not to use metal hybrids because of the fact that they are endothermic. They can be in the cold already. A few other reasons. They're not quite as developed for a situation like this. Cells with gaseous hydrogen seem to be the best option for these sort of conditions. So it's just a cylinder for ratings of very, very high pressure.
Okay, we're going to cut off the paper here, but I'm sure that they'll be around to answer additional questions for you and have a discussion.
Do you intend to come back next year with a workable prototype?
We absolutely intend to come back with at least a battery-powered vehicle. Everything else will be dependent, the fuel cell stuff will be entirely dependent upon discussions with SAE and MTU and whether or not it's allowed. We would never come back with a fuel cell powered snowmobile without full permission and full safety documentation. But we really hope to have an electrical start.
We got to move on to a dinner meeting. So.
Additional instructions for us?
Yes.